Hello, in a previous video we discussed the basic design of electrochemical cells and reduction oxidation reactions. In this video we're going to look at specific types of batteries that are used every day. We start with the simple Daniell cell, which was discussed in the previous video. It has all the elements that are present in commonly used batteries. We have an anode where oxidation occurs. We have a cathode where reduction occurs. The electrons flow through an external circuit from the anode to the cathode. And it's at, of course, the external circuit which generates the work that we get from the battery. Let's look at some specific batteries. We'll start with the lead-acid battery. And here in the lead-acid battery, we see on the left what happens while it's discharging. That means while it's in operation. The lead-acid battery, of course, is a battery that you'll find in your car. There are actually 6 modules within the battery that generates the 12 volts that is in the typical automobile. The cathode over here on the right the anode on the right is where oxidation occurs. And in this case, the oxidation is simple. We're going from lead 2 ion. So there's our oxidation. Electrons flow through the external circuit to the cathode where we have reduction. In the case of the reduction, what's going on is lead 4 ions that are present in lead oxide are reduced to lead 2 ions in the cell. Now, one of the advantages of the lead-acid battery, of course, is that it's rechargeable so that when your car is operating, the battery can be recharged to help at least extend its life for a period of time, perhaps several years, depending on the battery that you have within your automobile. So on the diagram on the right shows how the battery is simply reversed the process where in the case of discharging, electrons flow from the anode to the cathode. In the charging mode, we see that the electrons are flowing in the opposite direction to regenerate the substances that were present originally. So when the battery is recharging, of course, we reverse the process. So here on the left, this electrode is the anode, and you'll notice that it has a positive charge to it, and that's due to the fact that at that point at the anode where we have to force oxidation to occur, we have to we have to do work to get the oxidation to occur in that circumstance. And then here over on the right side, we have the cathode where reduction occurs to regenerate the original material. Here are the reactions, specific reactions that we see in the lead-acid battery. At the anode, and this of course is during the discharging phase, at the anode we have the oxidation of the lead to the lead 2 ion and lead sulfate, and at the cathode we have the reduction of the lead 4 ion to lead 2. And again, here's the overall reaction with the balanced electrons. 2 electrons are transferred in the process. Now, if we do a quick comparison of the thermodynamics of batteries, if we ask, okay, what would be the situation if we were using the energy associated with this reaction to generate thermal energy and do thermal work? Well, we can figure that out by going back to our discussion of the Carnot engine earlier in the semester and the efficiency of the Carnot engine, which is based on the temperature differential. So if we take the efficiency of the Carnot engine and multiply it by the amount of heat, the enthalpy change associated with the reaction, the work we would get would be negative 113.79 kilojoules per mole. So we could get work out of it with the exothermic reaction and the efficiency associated with the Carnot engine. That's how much we would get. On the other hand, if we calculate the amount of work we would get if it's electrical, we use delta G, because remember, delta G represents the maximum electrical work we can get from the system. So if delta G is negative 376.97, you'll see that we get quite a bit more work, electrical work, out of the system than would be the case if we had a thermal engine with a 300-degree temperature differential here in this circumstance. So the ratio then shows that the amount of work we would get thermally relative to the amount of work we would get electrically is 3%. So the electrical work is much more efficient than is the case if we were trying to extract thermal work from this exothermic reaction. All right, here's another commonly used battery. This is the alkaline cell battery. This is the one that you're probably using in some of your smaller devices. So in the basic design of the alkaline cell, we see that we have oxidation occurring, and again, you'll notice that it's zinc that we're oxidizing, and the cathode, at the cathode where reduction is occurring, you notice it's the manganese that's being reduced in this case. The manganese goes from a +4 oxidation state to a +3 oxidation state in this circumstance. So with this in mind, this is what we get for the reactions that are occurring within the cell itself. And this shows the basic design of the cell, where we've got the cathode, which is kind of a pasty manganese dioxide on the outer part of it, okay? And then we have the anode occurring here in this area where we've got powdered zinc. All right, so again, at the anode, the oxidation involves the oxidation of zinc, but at the cathode, it's reduction of the manganese and the manganese dioxide, as indicated here. So that's the simple design for the alkaline cell battery. Again, it's alkaline because you notice there are hydroxide ions present in the reaction. So now here's the nickel metal hydride battery, which is noted here is a battery that's used in hybrid vehicles. There's a metal alloy that's used in this situation. It's a metal hydride, and here we see at the negative electrode, which of course is the anode, where oxidation occurs. We get actually what's going on is that the hydride, if you take a look at this really carefully, it looks a little confusing because you'll notice that we've got a metal hydride here as a reactant species, and the metal actually is going from a plus to a 0, so the metal is actually being reduced, but most importantly, it's the hydride in this reaction that's being oxidized in this case. So that's where the electrons are coming from, and this shows here in this diagram at the anode what's going on. There is an alkaline electrolyte which allows the exchange that goes through between the electrode itself and the external circuit and the electrolyte. At the cathode, we've got another very interesting reaction that's going on at the cathode. So at the cathode, we have nickel ions that are actually being reduced in this circumstance. As you can see, the reactions in these batteries are getting more complex, and there is quite a bit of research going on to design more efficient batteries that generate more energy and that clearly are longer lasting. So this is a very, very active area of research these days. All right, now there's the lithium-ion battery, which is the battery that's commonly used in electric vehicles. And there is also a lot of research dealing with the materials that are used in these batteries. Here we have a situation where at the anode, we're actually getting oxidation occurring of the lithium ions at the anode, liberating electrons. At the cathode, we have this complex material which involves cobalt, and that's actually one of the concerns. There's some research being done to try to develop new materials that are more environmentally friendly in these lithium-ion solutions. And so we'll note at the cathode, then we've got the reduction going on. The maximum voltage for a single cell of these batteries is roughly 3.7 volts, and that depends on the electrolyte material that's used, as well as the cathode and anode materials too. So again, there's a lot of research in these areas. Obviously, an interest in developing electric cars requires that efficient batteries that generate high energy densities and can last for a long period of time is of utmost importance. So this is really a neat area of research going on right now. This shows kind of the basic design of some lithium-ion batteries, and where you will note that actually what you've got is kind of these layers going on in the material itself. We've got separators, and we've got these layers where these different layers have the materials undergoing oxidation and reduction. And I think on the next slide, in fact, I'm going to go on to the next slide. I thought I had it here. Well, so let me go back. I'm going to pause here for a second. Here we go. This kind of shows what's going on with these layers of materials that we've got. Lithium ions in the discharge state, and again, the discharge state is one where we are talking about actually having a situation where we're using the battery. Again, the charge state is where we're recharging the battery so that it gets repeated use. But in the discharge state, we'll see the migration of the lithium ions here in this situation from the negative electrode where they're produced to the positive electrode. Again, the negative electrode would be the anode, and the positive electrode would be the cathode. And this is, of course, a very interesting reaction because notice that the lithium ion actually is used. Let me go back one more here. The lithium ion is actually present in both the anode and cathode reactions. So that's a pretty critical issue that involves the transport of the lithium ion between the two electrodes in the lithium battery. And again, the substances that are used, the materials that are used, are actually quite critical for the performance of the battery itself. This slide just shows very briefly some of the things we've already discussed here in the case of the lithium-ion battery. Just noting that the anode is made of graphite. Graphite is a conductor of electricity, as we've talked about, and the cathode actually contains this lithium cobalt compound. And again, there's quite a bit of research that's being done on different materials that might be used for the purposes of these batteries, which are very important for electric vehicles. All right, so when we talk about the different materials that might be used for these electric vehicles, the energy density is a critical factor. And we want to know how much energy we can generate per kilogram of material, and also we want to know not only energy per mass of material that we're using, but also energy per volume, because clearly, particularly if you're using these batteries in small with small volumes, you want to pack as much punch as possible in a small volume. So the energy per volume is quite critical, as well as the energy per mass in the development of these battery materials. So if we move on then to take a look at some different materials that are different batteries, types of batteries, and their energy density. Along the vertical axis, we have the energy density per volume, and this is just WH is just watt hours. So watt hour is a form of energy. So watt hours per liter along the vertical axis, and watt hours per kilogram along the horizontal axis. Obviously, what we'd like to do is maximize both. And so we'd like to be over on this side of the graph, because we'd have a maximum energy density volume-wise and energy density mass-wise. The lithium-ion battery actually does quite well. The different materials, this shows that the variation of lithium-ion batteries, and actually it can get quite a high energy density per volume, as well as a reasonably high energy density per mass. In fact, the only battery that exceeds the energy density per mass, joules per kilogram, is a lithium metal battery, but it does not have the energy density per volume that the lithium-ion battery does. This diagram shows the potential generated by the lithium-ion battery with different types of materials. And we were talking about, for example, 3.7 volts as being on the order of the maximum associated with this. So we're talking about in this region here, 3.7 volts. Again, there are different materials that are being used, different types of electrolytes that are being used, and electrodes that are being used and developed to help to maximize the output of these batteries. And of course, this is a slide we looked at earlier where we're talking about the lithium ions migrating from the anode to the cathode in the charging state and reversing that in, migrating from the anode to cathode in the discharge state and reversing that in the charging state to recharge the battery. And now the final battery we're going to talk briefly about is what's called a fuel cell. And the fuel cells, these are actually batteries, for example, that are used on the space station, the space shuttles. They just simply take place as you see the basic reactions here for these fuel cells, depending on the type of fuel cell, simply involves the process. Let's go back. Okay, just simply involves a process that you can basically see here on this, where we're talking about the oxidation of H2 and the reduction of O2. So the basic reaction involves H2 reacting with O2 and generating water as a product of that reaction. So these cells have the potential to generate quite a bit of energy and quite a bit of work, but there of course are issues with how do we design these cells, how do you handle the hydrogen, what are we doing with that. So there's still a lot of areas that are being done. The mechanisms here show on the one that's in green is actually, these are the most commonly researched right now, with proton exchange membranes, which allow the passage of H plus from the anode to the cathode internally in the cell. But again, there's a lot of research being done on the different types of materials that are used as the electrolyte that allows the passage of that. How do we store the hydrogen? For example, in this case, the hydrogen is actually generated from methanol. In this case, we see a reaction which involves enzymatic extraction and oxidation of the hydrogen. And again, there are various designs here that are shown in this diagram that are being used and developed to help maximize the potential of these fuel cells. There certainly was a time, and there's still discussion about developing fuel cells for automobiles. There's competition, obviously, between electric cars, which use lithium-ion batteries, and those which use fuel cells. Again, some of the issues associated with the development of fuel cells, how is the fuel stored, and those issues which still have not been fully worked out, that lead to some of the questions associated with that. Of course, in the case, one of the advantages of fuel cell over a lithium-ion battery used for transportation is that it takes time to recharge the lithium-ion battery, whereas if you've got a fuel cell, you could simply imagine having fuel stations similar to the gasoline stations that we have now, that you could stop along the road and fill up. But again, how do you do that? How do you do that safely is a question that researchers are still developing and thinking about. And this diagram here finally just shows in a little bit more detail what might be going on within the fuel cell, so that we have on the left the anode, where the oxidation is occurring, and then we've got the catalyst, the surface catalyst here to help to catalyze the reaction. The H plus passes through the membrane to the other side, where we get the reduction of O2. And again, we're going to get electrons flowing externally from the anode to the cathode. And here, this diagram just shows some basic information about fuel cells and the temperature, the optimal temperature which they operate in the different types of cells. This is something we can talk about in more detail in class. I'm just going to move on to beyond that, and this ends our brief description of some types of batteries and their design. Again, this is a hot area of research. If you're interested in this kind of thing, there is a huge need, obviously, to develop alternative energy sources, and batteries are one of those alternative energy sources that we can be talking about. So there is quite a bit of very interesting research going on in these areas. So this concludes our brief introduction to electrochemical cells. We'll talk more about this in class.